So basically, solar panels require semiconductors to absorb energy. But right now, the semiconductors we're using are extremely inefficient and expensive. The industry standard is silicon, but it's very costly. And as a result, American energy consumption is based only 1% on solar power, even though it's a very renewable and green energy form. The ASU Newman Group developed a new method to develop pyrite, which is a material that is about 10 times cheaper than silicon and is a lot more effective. However, when they were growing these pyrite thin films, there were defects in the thin films, and they had no way of distinguishing between the contaminated thin films and the clean thin films. So if the contaminated thin films were put into solar panels, that would cause defects. I developed a method using optical testing to distinguish between the contaminated thin films and the clean thin films. Silicon is extremely expensive, and it only has an efficiency rate of 10 to 25%. However, scientists largely agree that by incorporating iron pyrite into these solar panels, we would make these solar panels a lot more efficient and a lot cheaper. So I was motivated to follow this project because I've always been very environmentally conscious. In fact, I don't even eat meat because I'm always looking at the environmental implications of my actions. And basically, before this project, I was studying the sustainability of schools in our communities and looking at how we could reduce their greenhouse gas emissions. So I also wanted to look at optimizing solar panels so that more Americans can afford them, so that our world can have a greener future. I looked at the spectroscopy results of these iron pyrite thin films, and spectroscopy basically measures the reflection spectra of these thin films across an energy range. And I've been able to develop a method to identify the bandgap energy of these films, which is the amount of energy these films need to excite electrons to the next stage and absorb energy. So now researchers and manufacturers can determine the bandgap of these iron pyrite thin films and determine if these films can be used in solar panels or not.
Initially, I turned to UV-vis spectroscopy to understand the bandgap of synthetic and natural iron pyrite. The bandgap is the amount of energy needed to excite electrons from the valence to the conduction band, or in other words, to break an electron free of its bond. When an electron is excited from the valence to the conduction band, the absorbed energy is reflected. Absorption only occurs when the photon energy exceeds the bandgap energy and should remain zero below the bandgap, since electrons will not jump to a higher energy level. Ideally, iron pyrite films used in solar cells should have a bandgap of approximately 0.95 electron volts. I was able to show that it is possible to use a reflection spectrum of an iron pyrite sample to calculate bandgap. Since absorption below the bandgap is zero, reflection is constant below the bandgap and begins increasing after the bandgap energy has been achieved. By calculating the bandgap through optical testing, manufacturers can discard samples with the improper band structure. Previously, this line of reasoning had not been applied because researchers had assumed that contaminants would completely alter bandgap and absorption structures. I was also able to turn to computer modeling in MATLAB to show that any reflection peaks before the bandgap had been achieved indicate the presence of contaminants. Throughout this process, I grew greatly in my ability to code and to integrate computational and experimental results to draw conclusions. Along with the presence of contaminants in iron pyrite, a major hurdle faced by manufacturers is isomer growth, as the ions in iron pyrite films occasionally misalign. The initial success of my spectroscopy work prompted me to turn to ellipsometry to evaluate the potential for optical testing to detect the growth of marcasite isomer in films.
My project shows that optical testing can be used to distinguish between iron pyrite films with marcasite contamination and clean iron pyrite films. So basically, by using ellipsometry, we can measure the extinction coefficient, which is a function of energy and is also proportional to the absorption of light of these films. So for a film without any marcasite contamination, there's going to be a peak at about 300 nanometers in the extinction coefficient spectra, and there's a signature band structure at 500 to 600 nanometers. However, when there is marcasite contamination, you don't see these features as clearly. So now manufacturers can do a simple ellipsometry test on their pyrite thin films and determine which films can be used in photovoltaic cells and which films can't.
Once again, I was able to integrate computer modeling, MATLAB, and my optical data to create a framework capable of detecting marcasite contamination. Throughout this process, I grew as a coder and as a researcher capable of using both computational and experimental data to make significant conclusions. This project relied heavily on fundamental theories. Basic quantum theory indicates that electron energy is quantized and absorbed in multiples, suggesting contaminants alter film electrons' optical energy absorption patterns in a standardized fashion. Hence, optical testing could theoretically distinguish between clean and contaminated films. After 2 years of optical testing on pyrite films, I developed a generalized method to accurately identify contaminant concentrations in films and prove that each contaminant triggers standardized energy absorption and that absorption patterns could also be observed to evaluate marcasite contamination. I saw the power of focusing on fundamental details. Applying basic quantum theory allowed me to develop a method to identify usable pyrite, enabling manufacturers to mass produce pyrite-based solar panels and potentially save billions annually at scale. This project is unique as it combines basic laws of physics with advanced computer modeling to make tangible differences in our world. It suggests that the combination of optical testing and computer modeling will allow for the identification of inexpensive, environmentally friendly, non-toxic materials that can revolutionize the production of renewable energy. This suggests that similar models can be used for other materials that can potentially be used in renewable energy sources too.
So in the future, I would like to continue my project by studying the electrical properties of marcasite and iron pyrite to try to develop a faster and more efficient way to distinguish between iron pyrite and marcasite contaminated thin films. Also, I would like to use my general optical testing method to study other materials and see if they can be optimized too. This project actually has a lot of real-world benefits because in 2015, the solar panel industry was valued at over $37 billion. However, because silicon is so expensive and iron pyrite is 10% as expensive, this project will allow manufacturers to save billions annually at scale, and it's going to allow consumers to buy solar panels at much cheaper prices, which should reduce our reliance on the depleting fossil fuels that affect the atmospheric ozone layers. In the future, I would love to major in environmental systems engineering and receive a PhD in material sciences so that I can be a researcher in sustainability and also be a professor at a university. I think that this job would really help me show the next generation of STEM leaders how research can really empower us to make tangible differences in the world, and I can also help make our future a greener and more sustainable place by researching sustainable operations.